First, some background about sizing. So what is a fiber sizing? Like we applied all the different textile materials, including carbon fibers. It's a very thin and homogeneous coating applied on the surface of fiber, then to protect the filaments during handling, processing, and compounding and composite processing. So in the composite, it can improve adhesion between the fibers and the matrix, and also it can increase the mechanical properties, chemical or water resistance, and the thermal stabilities. So if you can look at this photo here for the sizing from Michelin, you can see the difference of sized carbon fibers and unsized carbon fibers. So during the process of the carbon fiber manufacturing, there's a PEM, precursor, oxidation, carbonization, surface treatment, their process of sizing, then it's carbon fiber spore winding. So during the recycling process, solubilisis or pyrolysis, the original sizing in most cases is removed. So when we want to reuse this recycled carbon fiber, there's also a problem adhesion with matrix. And so it leads to our bent composite qualities. That means low mechanical properties. So the solution in this project is we want to apply a resizing formulation, a new coating of this recycled carbon fibers. But there are some challenges. That means if we want to reuse this recycled carbon fiber in different matrix, so we should develop different sizing formulations. And also we need special formulation for recycled carbon fibers. And normally for the different company of recycled company of carbon fibers, they have different formulation, but normally they keep it separate for each companies. So we don't know very well the formulation. So we want to develop in this project. Recarbosize. So it's a resizing recycled carbon fiber to optimize adhesion with polymer matrix and improved processing behaviors. So the coordinator of this project is TFI. Then we have partners of IPF, and CENTEXBEL is a partner of this project. So in principle, STFI is to develop the reinforcing textile structures, the nonwoven structures based on this recycled carbon fiber. Then for IPF, they develop the defined sizing formulations for thermoplastic matrix, then to try to apply on different carbon fibers, then test into composite in microscales level. In CENTEXBEL, we develop a suitable sizing formulation for thermosetting matrix, then applied on single carbon fiber, then characterize them, then show the potential of sized recycled carbon fiber in composite applications. For example, in the matrix like PU and epoxy. Here I want to focus on epoxy matrix. So this some point I want to discuss in this presentation, and how we develop the sizing formulations, and how to characterize on single carbon fiber, and a feasibility study of reuse this resized recycled carbon fiber in composite. So we use 3 different characterization methods on this single carbon fibers. The first is the Fibres test. It's a kind of tensor test, but on single fibers. If you can look at this photo. And on this machine, we can measure the linear density of the carbon fiber, and we can obtain the force as a function of elongation, so we can estimate the tensile stress and Young's modulus of this fiber. Of course, SEM, we can measure the diameter the surface structure and chemical composition by SEM-EDX. And by using TGA, we can measure the amount and the rate of change in mass of a sample as a function of temperature and the time in a controlled atmosphere. So first, by using Favima test, maybe I can show a small video. It doesn't work. So, okay, the fiber is suspensible on this two head of this machine. Then it gets us more force to make this tensile test. So we can get the force and strain curves. So we can see that at the first stage of these curves, it indicates a linear and elastic behavior to break for these carbon fibers. So we can use the slope of this curve to estimate the tensile stress and Young's modulus. Good. Okay, so this is process of the tensile stress. Then we compare the recycled fibers before and after pyrolysis. Before pyrolysis, we can see the fiber shows a smooth surface, but after pyrolysis, we can see a lot of dark areas and a small amount of residues on the surface. So it's a damage on the fiber surface by the process of pyrolysis. And also by compare the chemical composition, we can see on original virginal fiber, we can have the carbon, oxygen, the potassium, but after pyrolysis, we can see the nitrogen is ended on the fiber surface is due to the process of the pyrolysis. Then by using TPA, we measure on the recycled fiber before and after solventlysis. On the top is before solventlysis, and on the bottom is after solventlysis. We can see the residue on the surface is visible, and the mass change is visible. There's a very high variance in the result before and after solventlysis. The amount of size from 1.25 to 2.78% by weight, then decrease to very low level. So that means the original sizing is generally removed during the solventlysis process. So now in the first time, we try to purchase the different kind of recycled carbon fibers in the market. Then we compare them in different properties like linear density, the diameter, the elongation, and elastic modulus. But the problem is the exact composition and original type of fiber can't be determined. So it's difficult to compare them. So in order to ensure a good reproducibility and the comparability of the test, we decided to purchase the carbon fiber waste by ourselves. Then we sent it to our industrial partners to do the pyrolysis to remove the original sizing and to simulate the recycling process of end-of-life composite. So here you can see the result. Again, we compare the linear density, the diameter, elongation, and elastic modulus. We can compare first the virgin fiber we measured by our method with the technical sheet we received from the product producer. And we can see all these parameters are comparable. So that means our method makes sense. Then we measure again on this recycled carbon fiber with the same original fiber by pyrolysis. We can see the linear density decrease, the diameter is almost the same, and the mechanical properties, elongation, and elastic modulus decrease. So in the future, we will use the same recycled carbon fiber for our sizing development because we can compare with the virgin fiber. So for the sizing formulation, we know that there's a different ingredient There's water, film former, the weighting agent, coupling agent, lubricant. Sometimes we should add anti-foaming agent. So we try the different kind of ingredient for define a good sizing formulation, and we try to develop a process for applying sizing on individual fibers and characterize them. So here I show you some examples of this film former dried on plastic foils. We can compare the film former 1 and the film former 2. We can see clearly that the film former 2 don't have a good homogeneous properties. The film former 1 is better. Then we compare the film former with weighting agent or without. We can see that by optical microscopy, the film former with weighting agent has a better homogeneity on this morphology. Then we try to separate the individual recycled carbon fibers by a Favimat collapse and hung on one support we developed in our lab. Then to immerse all these fibers into the formulations solutions that we dry in the air overnight, then sent to the characterizations. So you can see some result. By SEM, we can compare the unsized carbon fiber and resized carbon fiber. We can see the surface is more homogeneous than unsized fibers, and there's a small layer of the film former on the fiber surface. But when we compare the mechanical properties, the elastic modulus, the first column is a virgin fiber, the second is recycled fiber that we compare with 4 different sizing formulations, but there's no evident effect on these mechanical properties. So I would say there's no big influence on the mechanical properties for itself, the single fiber. But to measure the adhesion force with epoxy resin, there's 2 possibilities. The first one is the pour out test of the single fiber. That means we put one single fiber in a drop of a resin, then put it out of the resin. But for this moment, we don't like we don't have this method. So we try on the second possibility, we reuse all these fibers to produce the composite. Then we to do the mechanical property test on this composite to get to know the adhesion force of these fibers with epoxy resin. But before use these fibers in the composite, we want to check the thermal stability of the sizing by TGA. So we can see on this curve, with the temperature increase still about 900 degrees, there's 3 stages. The first stage is about 200 degrees. The water starts to be evaporated. And the second stage is the contamination of the surface and the sizing start to be degraded. Then the third stage is the fibers, carbon fibers start to be degraded. So that means the sizing formulation is still stable at 200 degrees. So in our composite manufacturing, we were used infusion, vacuum infusion. The temperature is about 40 or 50 degrees. So the sizing can be stable in this temperature. To reuse this resized carbon fiber in composite manufacturing, STFI is tried to fabricate different nonwoven structures. You can see here, there's a 100 percent of the recycled carbon fiber, and also the recycled fiber mixtured with polyamide fiber with different percentages. Then we applied selected sizing formulation of these nonwoven structures. Then we consolidate all these fibers into composite by infusion, vacuum infusion method, with epoxy. Then we get all these samples, composite samples. Then all these samples are sent to the interlaminar shear stress test, RLSS test. So it's to measure the resistance of the composite to delamination on the shear forces parallel to the layer of laminate, and so to the adhesion of the interface. For each samples, we test 10 samples by direction. So then to calculate the average value of the shear strength. So now I show you the first result we have. We compare the shear stress of the different composite by different sizing formulations. So the first column is the composite without any sizing, is just the recycled fiber. And the second and the third is the virgin carbon fibers, just after tearing the fibers, so we can consider as a virgin fiber. And the last four is the different sizing formulations. From this graphic, we can have different conclusions. The first is we can see clearly the recycled carbon fiber composite has a higher shear strength comparing to the unsized recycled carbon fiber composite. We can see an increase of 19% of shear strength. So that means adhesion is improved by resizing formulation. If we compare this recycled carbon fiber with virgin carbon fiber, yes, it makes sense. The virgin carbon fiber is higher than recycled carbon fiber, but that means we still space to improve our sizing formulations. So if you remember, we test also the different percentage of carbon fibers in the nonwoven structures. So here we compare the 20%, 40%, and 100% of recycled carbon fiber. Again, if we compare in one kind of composite, we can prove again the resized recycled carbon fiber composite has a better shear stress than unsized recycled carbon fiber composite, and also with increase of the carbon fiber percentage, there's an increase of shear strength. So now we can come to our conclusion. The first, resizing recycled carbon fiber can enhance the shear strength of the final composite, and there's no significant impact on the mechanical property of single fiber itself, but the sizing can enhance adhesion force between the resized fiber and epoxy fiber. But after we want to investigate by the pour out test to really measure the adhesion force between the fiber and epoxy. And the third is reusing resized recycled carbon fiber in composite with various nonwoven structures is feasible. And with the increase of percentage of recycled carbon fiber, the shear strength of the composite improves. So that end. Thanks to the partners and also our colleagues and the financial support from Cognet and the Wallonia region. Thank you very much.